Hello. So I'm cobbling this screencast together at the last minute because I'm not going to be able to make it to the lab tomorrow. But I'd like to walk through the same stuff that I went over in class on February 21st with a Thursday lab section. And I'm going to start by, I'm probably going to overlap a bunch of things that are covered in the other Shell Lab screencasts. But I want to do this anyway just to give this kind of a logical flow. I'm probably going to make some mistakes, but hopefully, that'll help to keep it real. So I'm sitting in the Shell Lab directory, and I'm going to very quickly talk about the development approach you should take to the Shell Lab. So for starters, there are a few files that I should point out. Tish.c is where you're going to do all of your development, so all the code you're going to add is going to be there. And all of these files here, all these trace files, these are the files that you're going to be using to test your shell and to also aid in incremental development. Up here, we have a bunch of source files. You're not going to change these, but these are programs that you can use to test your file. And all the way at the bottom, here's an executable. It's the reference shell, and this is the one that you can use to A, run the traces against to see what your shell's output should look like, and B, just to sort of fiddle with to see how your shell should behave. So I'm just going to go ahead and start that one up. So if I do tshellref, you'll see that drops me to a shell prompt. And this is where you can try out commands. This shell doesn't use the path, so you have to type every command out with a full path. So if I do binls, for instance, it'll run binls. If I run binls with an argument, it'll do, for instance, here it'll do a full directory listing. I can do a process listing, for instance. It shows me that it is running, right? And obviously all the processes that I ran before are reaped because we don't see them here. I can also run, oh, I can't because I haven't compiled them yet. But I can also use my foreground, background, and jobs commands. So for instance, if I were to do sleep 3 with the ampersand character, that puts the job into the background. Oh, actually, it doesn't. There we go. Bin sleep, I think, is where it is. There we go. Now I have a job running in the background, which I can view as jobs, and it'll eventually terminate in 3 seconds. So if I do a jobs listing again, it's gone. Okay. Now, to do more interesting things, I'd like to compile those programs that I told you we have to help us test our shell. So I'm going to go ahead and quit out of the shell with the quit command. And I'm going to go ahead and do make. That's not only going to build my shell, which I'm going to add to code to in a moment, but it's also going to build these programs that I told you before are useful. We can use these to test our shell. And if you just look at a comment up atop each of these files, so for instance, if we take a look at myspin first, you'll see that this program sleeps for n seconds in 1 second chunks. We actually use this during lecture one time. So for instance, if I do myspin 3, and I'm doing this from my regular shell, my login shell, it'll sleep for 3 seconds. If we check out the comment atop my split, and I won't look at all of them, but just a few are interesting. My split forks off a child that sleeps for n seconds in 1 second chunks. Now this is kind of interesting. So if let me do this in the reference shell. So if I were to do my split 3, I wouldn't notice anything interesting because here the parent forks off a child, the child waits for 3 seconds or sleeps for 3 seconds, and then the parent just waits for that child to complete. Now what does make this interesting, let's go ahead and say let it run for a while. Okay, and I'm going to run it in the background. If at this point I do jobs, I see there's one job, but if I do PS, you'll see that there are actually 2 processes by the name of mysplit running, and these are both running in the background. And there are 2 of them because the parent forks off the child and they're both running the same program. If 10 seconds have already passed, the job is gone, and note that both of those jobs are now gone. Now what that tells us is this. It tells us that the job terminated in the background, and when both the parent and child terminated, the parent was reaped by my shell, okay, and the child also got reaped, presumably because the parent died and the child got reaped by the kernel. Now there's more to this story, because if I were to do my split 10, left it in the foreground, and then hit Control Z, which remember suspends a job or pauses it, and I now do bin PS, okay, you'll see, and actually let me do bin PS with dash T, actually, let's see, maybe dash S, bin PS dash S, there we go. Alright, so dash S gives me a status, okay, and note at this point that I have the T status next to both of the my splits. Okay, now what this tells me is that these jobs are both currently stopped. That's what the T means. Okay, now this is interesting because it means that when I hit Control Z, my shell not only sent that stop signal to its child, but it also sent it to the child's child. Now, the way it did that, of course, was to use the process group. Okay, so when I forked off my process, that child process had to found a new process group. When it created its child, that child was part of my first child's group. So my child and grandchild are part of the same group. I send them the sig t stop when I hit Control Z, and they both stop. Now, if I were to do BG, and at this point I only have one job in the background, so if I do BG %1, what that should do is it should resume both of these processes by sending the continue signal, which you'll read about in the lab write-up, to both of these processes. So let me do that, and very quickly do this, and we'll see both of these jobs are now running. Okay, they're both sleeping actually because they executed the sleep system call, but that's okay, right? Because eventually they're going to complete. Let's see, they have already completed. And indeed, I no longer have my splits in my process listing. Okay, so that's just one of the features of the, well, actually I demonstrated a bunch of the features of the reference shell. Keep in mind that your output, your behavior of your shell should mimic the reference shells almost to a T. Okay, now the way you should go about developing your shell, however, isn't to just randomly test out features of the reference shell and try and get your shell to match it. Instead, you're going to be using these trace files, 1, 2, 3, 4, all the way through 16. Okay, and you're going to incrementally move through them and try to get your shell to work on each trace file the same way as it would, as the reference shell would handle these trace files. And again, I talk about this in the other screencasts in much more depth. But to use these trace files, well, first of all, let's see what they look like. So if I print out the contents of the first trace file, it shows me 2 of these all caps commands. These all caps commands aren't actually sent to the shell itself. Instead, they're sort of meta commands that the test driver program knows how to execute. So close just means, in this case, to send an end of file signal to the shell, and then wait for it to close properly. So what I can do is test that trace file on the reference shell by doing make rtest01. And this is what the reference shell gives me. None of this is actually output by the reference shell. We'll see in a little bit later on some of the trace files actually show me output. But what this tells me is this output is the output that should be generated when I run this trace on my own shell. So when I do make test01, this time without the R, I'm going to be running this trace file on my own shell. If I do that, I get exactly the same output. Now this tells us that our shell behaves in the same way as the reference shell. Incidentally, that also tells us that this trace is working. And in fact it is. You don't have to do anything. The first trace works by default, okay, because the shell that you're given already terminates on end of file. Now we can go on to the other one. So let's try and make rtest02. Okay, so I still get no output. If I do make test02, now unfortunately that doesn't behave the same way. So you can see that my shell is not behaving right. The trace says process built-in quit command, and apparently my shell doesn't know how to process the built-in quit command. So I'm going to hit Control C to interrupt the driver and to drop out of this. So obviously I have to figure out how to make my shell respond to the quit command. Now, if we check out the trace itself, 02, you'll see a lowercase command, and this command is actually going to be sent to my shell. Okay, and quit, it turns out, is in the category of built-in commands, which is to say that my shell doesn't actually need to fork and exec anything. It just needs to detect that in the command line and respond to it. And respond to it in this case means to exit. So I'm going to go ahead and jump into the shell. And I'm not going to spend too much time introing the shell, because you can read about that in the lab write-up, and you can also watch the other screencasts. I want to keep this as short as possible so people actually get to the end of it. A few things, though, just a few things. General constants, I'll be using some of these. I've got a bunch of variables, global variables. I won't really need to use any of these, but I will need to use this structure here, right, in a little bit. This is the job structure. Now keep in mind that my shell is going to need to run a bunch of processes simultaneously, at most one in the foreground, but potentially many in the background, some of which can be stopped, some of which can be running in the background. And in order to keep track of all of them, I'm going to use this structure here, this job_T structure. Each entry in this array of job structures right here, each entry is going to contain a PID, a job ID, which is an internal identifier. You can see here it starts with 1, 2, etc., and a state, where a state is going to be one of these values: foreground, background, stopped, or undefined if that particular job entry isn't being used. In addition to state, I'm also going to keep track of the command line that was initially used to start that particular job. All right. So following that in the file, there's a list of the functions you have to implement. Okay, so this is a very focused lab. You're told precisely what functions you have to implement. Okay, and as you look down the source code, you'll see that obviously the bodies of these functions have no implementations. There are many other functions, however, that are provided for you, include parseLine. We'll see how that works very soon, and a bunch of functions that are used to manipulate the job list, which is the array of job structures, okay, and so forth. So it's in your best interest to go through and look at these functions yourself to see what they do. The main routine. A few things I should mention. First of all, you never need to register a signal handler explicitly, because they're all registered for you already, although you do need to provide the implementations. And here we have the all-important read eval loop. Remember, I described the shell as a REPL. Here we have essentially the heart of the REPL, where the shell prints out a prompt, the tish greater than sign prompt. It reads the command line, and then it proceeds to call the eval function with that command line, which is simply whatever the line terminating in a new line that we read from standard input. Following this, we have the eval function. This is where you're going to spend, well, not the bulk of your time, but at least initially you'll spend the bulk of your time here, because this is where we're going to be processing the input from the user. All right, so before I write any code, it's worth it to figure out what we have when we arrive at the eval function. So I'm going to go ahead and so keep in mind that as you work in the shell, and this is true for all the other labs this semester, you should really stick to writing just a few lines of code and then trying to see if it builds, and better after it does build or not. Of course, if it doesn't, come back, try to make it build. But if it does build, test it immediately. If not with a trace file, then at least by trying to use the shell, okay, and type something in and see how it responds. And that way you're never stuck in a situation where you've written 100 lines of code and the thing segfaults on you. So I'm going to go ahead, since I'm in Emacs here, I'm going to GDB the program. I'm going to debug the program, okay, from within GDB. And within GDB I can type make. It's already freshly made because I haven't made any changes. So I'm going to go ahead and set a breakpoint at eval, because that's a function I care about, and run it. Okay, so let me just go ahead and type something in. Remember that what I'm trying to do right now, let me switch back to my trace file. I'm trying to process the quit command. Okay, so let's see what happens if I type quit in at the prompt. Okay, let me change this a little bit. Okay, so I've got my debugger in the right, and you can see on my left-hand side I have the eval function with the breakpoint set in it. Okay, so clearly my eval function is not going to do anything. It's going to return immediately. But on the right-hand side, you can see already that once I hit the breakpoint, the debugger shows me I'm sitting in eval, right? So this is the stack frame I'm in, or the function I'm in, and you can see that the command line is currently equal to this right here, quit followed by a new line. Okay, I can also print out command line if I wanted to see it, and it shows me exactly the same thing. Okay, I'm printing out the name of a local variable in the function I'm in, and it shows me the value of it, which is quit followed by new line. So all I need to do at this point is, I could hack it up real easy. I could just test to see if I have quit followed by new line and quit the shell, but I'd like to do a little bit more than that. Because in the future, I'm going to go ahead and continue here. I want to be able to process a command like ls-l, right? And if I hit ls-l, I'm going to arrive in eval, and notice I'm going to have this string ls-l all as one long string with a new line, which is useless because, let's do another example. If I were to do something like ls-l-a, okay, I want to take all of these three tokens separated by spaces, okay? I also want to get rid of the new line, and I want to build an argv, an argument vector, okay, that I can use to exec that program. In order to do that, I need to do all this tokenization and parsing, but the good news is you actually don't need to do any of this. The reason you don't have to is because, well, it's done for you already. Okay, you're given a function, it's called parseLine, and I'm not going to bother looking at the implementation. I think I actually talk about it in the other screencast, but just very quickly. So it says, parses the command line and builds the argv array. Okay, so it takes an argv array, one that has presumably enough entries to hold the pointers, okay, to the various substrings within command line. And it says returns true if the user has requested a background job, false if the user has requested a foreground job. Note the int return value is either true 1 or false 0. So let's go ahead, go to eval here, and let's start coding this up. So you're gonna have to take my word for it, but I'm gonna need to define an array here. Okay, and I think max args is what I want. Max args, that's correct. So max args, all right, is the maximum number of arguments I can get. And I'm going to go ahead and call parseLine here. And remember that parseLine returns an integer telling me whether it's a background job. So I'm just going to call that bg and call parseLine like so. And I need to give it the command line as the first argument. So let's go ahead and do that. And I need to give it my argv as a second. Okay. All right, so that's one line of code. Let's go ahead and make this, and let's try running it again. And let's see what happens if I type in something like ls-l. Okay, so I'm sitting right now at this line about to execute it. Okay, so I'm going to go ahead and run that line, and now I've returned from parseLine. I'm about to return from eval, note in the left-hand side. So if I go ahead and check out argv, okay, oops, I didn't want to do that. Let me look at it component by component. So if I look at argv sub 0, it'll show me ls, which is marvelous, really. So it meant that it parsed that out. If I look at argv sub 1, okay, I've got -l. And if I look at argv 2, that's 0. Which is to say, I've got the first command line argument, ls, the second, and the argument vector itself is terminated by null 0. And if you remember this from class, this is precisely the format that is expected by exec, the exec v variants of exec, to be precise. All right, so I'm actually good at this point. All I need to do is check to see if my argv, and remember, again, I'm trying to handle my quit command, right? So all I need to do is check to see if my argv is equal to quit, right? But of course I can't do it that way, right? I can't compare pointers like that. So I need to do a string compare on quit Okay, and if it produces 0, it means they're equal, and if they're equal, then I simply need to exit, right? So let's make that, and let's run it again, and let's try typing quit. I'm now in Eval. Let's hit continue, and sure enough, it exits. Okay, and at this point, let me go here, and let's try make test 02. Bam. It works precisely the way our test 02 does at this point. So I've now handled my quit command. Now, this breakdown, however, I don't want to start inserting all of my built-in command handling code here. As it turns out, I've actually got a function down here called built-in command that's supposed to handle these built-in commands. Now, quit isn't a built-in command that's going to allow me to return from built-in command. Obviously, quit is just going to quit my program. But there are a bunch of other built-in commands. I demonstrated some of them previously: fg, bg, jobs, etc. So I need a test for those, and in fact, if I handle them, then I need to return true for the argv being a built-in command. So let me go back here to eval. So in truth, this code really belongs in my built-in command function, right? So I should be passing the argv along here, and this is where I'm testing, okay, that particular argv. Now, this is also where, incidentally, I would test the other built-in commands. So, for instance, I could test for the foreground command, right? And if that were one of the commands I received, then I certainly wouldn't exit, right? But I would handle the foreground command, okay? And then after handling the foreground command, I would return 1 to indicate that in fact it was a built-in command. Okay, and in fact, you know what I'll do? Let's go ahead and add clauses for the rest of them. Right, so I should have my background command. I should have my jobs command. Of course, this comment is incorrect. Right, and so forth. So if any of these clauses return true, then ideally, not ideally, then what I should do inside my eval is I should no longer exec and fork a process, right? Fork a process to exec a command. So here's what I'm going to do. Let's go ahead and check to see if the argv, okay, the first string of the argument vector, that is in fact a built-in command. Okay, and if it's not, this is in fact, oops, missing a parens here. This is in fact where I would need to fork and exec, right? The specified program. Okay. Otherwise, I would have already handled the built-in command. So I've modularized my program a little bit. Now let's make sure it still works. So let's go ahead and make it. And let's see, it made a couple of things here. Yes, not just passing my first item. Built-in command actually expects the whole thing. Make sure you watch those warnings there. Okay, so just an unused variable. I'm cool. So let's go ahead and try to run this guy. Let's type quit, continue once I break it eval, and bam, it still exits normally. Okay, and let's play with my T-shell a little bit just to see what's going on here. Actually, before I do that, let's quit out of it. And let's add a printf here. So forking and execing. All right, so we know this is where we're forking and execing. Let's do a make tish. And at this point, if I were to do something like, let's say ls, right, this is where indeed I should be forking and execing the ls program. Haven't done it yet, but I know that's where I'm supposed to do it. On the other hand, if I were to type a name of a command like fg, which is the name of a built-in command, note that I shouldn't be forking and execing anything. Okay, so I'm not actually handling these things, but at least I detect that it is in fact a built-in command. Similar thing happens with jobs, but on the other hand, if I were to type in something like bin ps, I would in fact fork and exec that. Cool. All right, so let's go a little bit further. So let's actually do the forking and execing. Forking and execing a process is something we've done many, many times, of course, right? And we know that in general, it'll look something like this, right? And if I get in here, then it means that I'm in the child. Okay, and since I'm in the child, that probably means I need to call exec. Okay, now I'm going to use the exec VP variant of exec because I know that that's going to take, for starters, it's going to take a path to the command, which is simply the first string inside the parsed command, the parsed argument vector. And it's going to then take the entire argument vector as the second command. The P portion means that it's going to look things up in the system path, which will make it easier for me to type in commands. And it's not going to break our trace files either. Remember that exec shouldn't return if running the new program was successful, because it kills off the current program. On the other hand, if it does return, then it probably means that the command wasn't found. Now what we should be doing is we should be checking to see what tshellref does. So it prints out the command line. Let's see if we do multiple strings what it does. So it just prints out argv sub 0 command not found, right? So we should in fact just use that, right? So let's copy that and really get this down. So let's see, %s, right? And let's just print out argv sub 0. Okay. And at this point, since we're in the child still, we certainly don't want the child to continue and then execute the shell. Instead, the child should terminate. Okay, so I'm going to do this, and I'm actually going to delete my breakpoint because I don't want the breakpoint anymore. Okay, let's go ahead and try to run this. I'm at my tish, and let's try running something that makes no sense. Okay, ignore this bit of output here. This is actually a GDB output that's telling me that it forked off a child process. This is the output from Tish. Now it doesn't quite look right. Note that I get back LKJS command not found. That is indeed correct, but for some reason the output happens after my shell prompt appears. That doesn't sound too good. Okay, let's try this again. Let's try it this time with a command like ls that I know should work. And so, all right, so the output from ls does show up. This is a good thing. Okay, but note, and maybe this isn't so clear here, so let's do it here. Let's quit out of this and let's run it again. So if I do ls, you'll see that the output appears, but it appears after my prompt. So what's going on here? Well, what's going on is this. Note that after I run my process, the parent process goes ahead and it returns from eval and prints out the prompt in main. It's not waiting for the child, right? And note I should be waiting for the child unless, of course, it's a background process, right? So here we go. So if it's not a background process, okay, then I should really be waiting for my child, right? Now let's hack this together real quick and just do that with a wait null. Okay, and what that means is wait for a child, right? Now this isn't an ideal solution, but for now it'll do. So let's switch over here. Let's try to do a make. Let's run tish and let's run ls. And sure enough, right, things look pretty good. Okay, indeed, it'll handle ls-l, it'll get the output, and then I get my shell back. So let's go ahead and check out trace. I think we're on trace 3 now. Yeah, we are. So trace 3, and I apologize for not checking the trace in advance. I kind of jumped the gun a little bit because I knew it was coming. Trace 3 tries to run a program, okay, with 2 arguments here. And this program actually has a sort of a dual purpose. So running this asks the shell to print this out, okay? And you know what? I'll just go ahead and run this so you can see what it does when I run this trace on the reference shell. So the first command causes tish quit to be printed out. And the second command, quit, is sent to the shell, which causes the shell to actually quit. Okay, so there are actually 2 programs, 2 commands being issued to the shell within this trace. Let's see if it works with my most sort of recently updated shell implementation. Sure enough, the output is precisely the same. So in Thursday's lab, I also talked about trace 04, so I'll do that too. Although I think you've already got a pretty good start. So trace 04, first of all, sends this to the shell, which will cause the shell to print something resembling this out, and then it sends this command to the shell. Make sure you understand what that means. Pause this if you have to understand what I'm saying here. I'm actually sending 2 different commands to the shell. Okay? And if you're curious about exactly what this means, you can always try this manually. So I'm going to run the reference shell, and I'm just going to copy and paste this. So let me copy that and paste it. And you'll see that when I run that command, this is its output. I know it looks a little odd, okay, but the reason we're doing this is so that you can see when you run the trace what happened within your shell. Okay, now the next thing I'm going to do is run this command. I just copy that, I'm pasting it, and that'll run that in the background. It'll run it in the background, and 1 second later that'll complete, okay, and then my shell will exit. All right, is what will actually happen. Now, since I'm doing this explicitly, I can also do a bin ps to see if the process exited. It did, okay, and I can quit from my shell. I quit out of it by using the end of file character, which is Control D, sent by Control D. So we can see this here, right? This is the output of the reference shell, and I can do it again by just doing make rtest 0. I think I was on 04. Okay, so this is what the shell should do. It should run the process, it should spit this out, and then it should give me back, then it should finish the trace. So if I try this with my own shell by test 04, well, it doesn't quite work the same way. And the reason it doesn't work the same way is because, well, I don't handle these background processes yet. Okay, and in fact, I can try this out. So let's run my own shell, and if I were to do my spin 1 ampersand, I get my prompt back immediately. There's no output. Distressingly, when I do bin ps, I'm now going to see. Let's see if I can. That's very bad, actually. Now I got a seg fault, right? All sorts of bad things happened. So now if we can think hard about this and figure out what happened, but it's not super necessary. What likely happened is that I had a background process waiting. And so this wait null doesn't necessarily wait for the most recently created child. It's quite possible that it waits for the child that previously terminated, right? Either way, this doesn't look good. I need to handle my background jobs correctly, right? I need to, if it is a background job, right, I need to print a status message, okay, something resembling, let's see, this here. Right? So this being the command line. Okay, this being clearly the PID. Now what is this, we might ask? Well, this is the job ID. The idea is that when I create a process, and it turns out it's not just background processes at all. Even foreground processes need to be entered into my job list so that I can track them. Okay? Every process I create should be added to my job list. Now my job list, I know I mentioned this earlier. Let's do another split here. Okay, and I'm going to jump to the top of my file. So you'll see, remember I've got this list of jobs in this jobs array, okay, where each job has a PID, a job ID, starting at 1 for the first one, okay, according to the comment, and then a state and a command line. Okay, now again, I don't need to manipulate this jobs list myself, not manually, because there are a bunch of functions here, including add job, delete job, etc. Okay, get job PID, get job JID for getting jobs by their PIDs and job IDs, etc. All right, that give me information about them. And if you go towards the end of the tish.c file, you'll see their implementation. Okay, so for instance, add job, which I'm looking for here, adds a job to the job list. Okay, and it returns 1 if successful, 0 if not. All right, so all of this is kind of useful, really. Let me skip back to the beginning here so we can have the list of utility functions. Here we go. All right, so I need to add a job after I create, right, a process. Okay, which means that, well, I need to do something I haven't been doing, which is to actually keep track of the PID of the process, right? So let's go ahead and do that first. So I need to store the PID of the process. Let me do that here. Okay, and now I'm going to need to call add job, right? So I'm going to need to add the job to jobs. I need to give it the PID, which I have. I need to give it the state. Now the state's a little interesting. The state is either going to be, and let's see, the state is going to be FG, BG, or stopped. Right? Those are the 3 possible values. Okay, they're defined up here: 1, 2, or 3. Okay. At this point, since I just created the process, it can either be a foreground process or a background process, and of course that depends simply on the value of BG. Okay. Now, an easy way to do this is just to use the ternary operator, right? The conditional operator. So if BG is true, I want a background process. Otherwise, I want a foreground process. Pause if you need to review what the ternary operator is and how it works. And finally, let's see. Whoops. Wrong one. Let's see. Add job also needs the command line, right? So I'm going to go ahead and give it the command line. Bam. And there we have add job. Right? Now, let's try and print out this pretty status message. So let's see. I'm going to need something that I'm going to need a printf, right? And I'm going to need to print a brackets followed by some number. I'm going to need to print an open parens followed by some number. I'm going to need to print a string. Right? So in this case, the first number is going to be, now here's where I actually need the job structure. So let me go ahead and create another job item. And note that I'm going to need to pull that out of my job structure. So let's see, job underscore t, right? Or I'm sorry, job is equal to, and I need some way of finding the job. So let's see, there's a multitude of ways of doing this, right? But one way looks to be get job with the PID. So how about get job PID, like so? Okay, and actually this should be a pointer to a job structure, because that's what get job PID returns. And get job PID needs to be given jobs, and it also needs to be given the PID that I stored. Right? So at this point, the job JID is simply JID, like so. I need the PID, and I also need to give the command line. Right? Okay, so let's see. Let's do this here, actually, for now. And let's try running the shell. Let's try doing something like ls with an ampersand. And there we have it. All right, there's my pretty little output. Okay. Unfortunately, I'm still not doing things quite right, right? Because it turns out that, well, actually I don't know that, but if I try and run a bin PS, okay, things are not going to function correctly because remember I still have that funky wait bug, right? Okay. So clearly I'm going to need a way, of reaping my background processes. But I also need to be able to reap foreground processes. Okay? So the way we should do this, and I'm going to cover this fairly rapidly. I think I motivated this a little bit better when I ran the lab on Thursday. What I need to do is make use of this job structure that I just added. Okay, so instead of actually reaping the child here, remember that I really want to keep my reap centralized. Okay, instead of reaping it here, I really need to reap it at the place that I discover my child terminated. And remember, on Unix, I'm sent a signal every time a job terminates. And that signal, of course, is a sigchild signal. And I already have a handler registered for a sigchild signal, and that takes place inside my sigchild handler. This is where I'm notified that I have a terminating child. Whether that child is a foreground process or a background process, the system doesn't care, right? In fact, there's no distinction to the system. As far as the system is concerned, if something happens to a child, I get notified here, right? So I'm going to need to get the child's PID. Presumably, eventually, I'm also interested in the status of the job, right? And I'm also ultimately, going to need the job structure for the job. Okay, so now hopefully I'm not giving anything too interesting away here. This actually comes from the lecture slides, but I'm going to go ahead and reap the child that terminated here. But I'm going to use the wait PID variant, right? So I already have a status. And remember that if I give this guy W no hang, that means that I'm not interested in waiting around if there's no one that's currently stopped. Okay, as long as that's 0, then I should be able to proceed and pull a job structure right out of this thing. So I'm going to go ahead and grab a job structure by doing, I think, what was it? Get job with PID, jobs PID, I believe, is a formulation here. And now that I've gotten the job, once the job terminates, naturally I'm going to need to delete the job, right? And I forget precisely what I need here. I need to give the PID of the job. Okay. Right? So I'm not really sure I need this. It doesn't appear that I actually need the job structure, but I do need to delete the job at this point. Okay, good. So I'm reaping the child. Yes. And back up here in Eval, I'm adding the job, so this is all good. So I add the job and I delete it in my sigchild handler. But there's one more thing that I need to make sure of. Note that I'm no longer waiting for my foreground job to complete. Right? That's gone now. And I can't very well do a wait null here. That would just be bad, because that would mean that my foreground job can actually get reaped in one of two different places, and that's simply not a good idea. Okay? Instead, what I need is I need some sort of function. I'm scrolling ahead because I know it's coming up here. I need some function that blocks until, and read this comment carefully, until the foreground process PID is no longer the foreground process. So if we give this guy a PID, the idea is this is going to wait until this PID is no longer associated with a foreground job. And what better way of doing that than to check the data structure that we've already created for this purpose. So here's where I'm definitely going to need a job underscore T. Right, and let's go ahead and pull my job out of here. So jobs PID. Okay, so I'm going to grab the structure. And at this point, I should check to see, right, if the jobs, let's see, PID is equal to the PID that I'm looking at. After all, this is my, right, this is my foreground job. Okay, so if the jobs PID is still equal to the PID, and furthermore, actually, what I'm really interested in is not so much if its PID is equal to the PID, but whether its state is equal to the foreground state. Right? Now, let's make sure that it is in fact state. I forget the name of the, yes it is, right? So I'm checking the state component of the job structure to see if it's still foreground. Okay, let's skip back here. All right, so now while that's true, so really if that's true, then I want to keep sitting around, right? Is what I want to do. Okay, and what better way to sit around than just sleep for a little bit? Okay, note that sleeps return immediately on signal, so this isn't going to be too bad of a performance problem. Okay, so let's see. I've got all this in place. I'm getting the job, right? As long as it's still the foreground job, I'm going to wait. Okay, all that remains to be done, it seems, is in eval. If it's not a background job, to call, right, wait with the PID of the process I just created. Let's see if that makes. Sure enough, it does. And this is that job variable I wasn't sure I was going to use. Let's see if this still works. So let's try a foreground process. Lovely, that works as it did before now. Right, I now get my command prompt back. If I try something like my spin, okay, let's give that 5. Let's run that in the background. I get my prompt back. I get this pretty output. Oh, I should get rid of the new line. Apparently I didn't need the new line. 5 seconds later, I should be able to do a PS, and it should no longer be there. It should be reaped. Right? Now, unfortunately, I can't list my jobs because I still haven't done that. Okay, but it looks like I'm much closer, right, than I was before. And we should be able to do something like this too, something that runs in the foreground. That should run to completion. I should get my prompt back. And just because I'm sort of obsessive compulsive here, let's go ahead and fix this prettiness, right? And let's try this again. Okay, this time let's try it with the test. So this is what test 04 is supposed to do. And here let's test it with ours. And sure enough, the output matches. We're done. Hope that was helpful. And I hope you have a nice snowy day tomorrow.